All right, welcome to kind of our intro to what is chemistry, what is science, things that you've done before. We're just going to go a little bit over for kind of our first true lesson of the year. So again, make sure to take some notes, jot some of this down. You'll probably be asked to answer some of these questions later, and also need to know this information as we get going. All right. First of all, there we go. What is chemistry, and why isn't chemistry important to me? That's always asked, all the time, every year. In the hard part about chemistry is just the fact that it's all around us. We can't see it. So if it's that small, it's just kind of going on. Why do I need to know about it? The fact is that not everything has to be a poison or an explosion for us to want to care about it, to need to care about it. And so the better understanding we have of chemistry, even if you're not going to be a chemist or a teacher of chemistry or in the medical field or, all those things that you probably think of right now that needs chemistry, just understanding things that you might read in everyday life, or you look at the back of a cereal box and you're like, man, is that good for me? Do I want to put that in my body? And you do some research and some of the words and things that you're looking at. The better understanding you have of chemistry, the better off you're going to understand life in general, but what's good, what's bad, and some of the things that you need to take a look at. So chemistry is all around us, and it's things we need to consider every day. Do we have to have a perfect understanding of chemistry, to get through our day? No. There was thousands of years where people didn't understand chemistry. But the better we do, the more we can understand how our body is reacting, how the world around us is reacting at the microscopic and the macroscopic level. All right. So in general, chemistry is the study of composition of structure and properties of the substances and the changes they undergo. Right. We study chemistry to see what happens. Right. Now the thing is, we don't always get to see what happens. Sometimes things are going on and they're just really, really slow. Right? Some things are so fast we don't even really see that there is a change. But it's going to be our goal this year to have a better understanding of, at that atomic level, at that molecular level, all these little things that are going on, what is actually taking place? Can we draw it out? That's going to be some of our goals. Can we think about some of the math associated with it? Not just the color changes and the heat and the light and the things like that are going to be going on. But if we can take a look at how it's made, what it's made out of, the shapes, right? That's where structure gets in, and some of the properties. The periodic table helps us with that. We understand a lot more. Okay? It's considered the central science, right? Why? Because it's literally at the center of everything. Living, dead, organic, inorganic, right? It's everything we could ask for to create life, to create anything. Something you'll hear me say all the time, and I've already said it in some of the classes, is, if we had a perfect understanding of chemistry, we could create anything we ever wanted, right? Combine that with physics, and literally we could create everything we ever wanted. So some different types. These you don't necessarily have to memorize, but just so you have an idea. So there is organic chemistry, which is basically carbon, hydrogen, and anything that's attached to them, right? So that's us. That's living things for the most part. Inorganic is basically everything that doesn't contain carbon. So kind of like the rest of the periodic table. We're going to take a look at both of those. Physical chemistry, right, is kind of when we get involved in energy and matter. We'll take a look a little bit of that this year. Biochemistry is when we take like the processes with the body. So like the energy that our body takes out of food, like how the chemistry of that, how does that go on? All right. So that is kind of organic, but it's much more specific. Analytical is kind of like the math side. And again, we'll take a little bit of a look at that too this year. Environmental chemistry, right? That's important in all of our lives. Trying to make sure that our environment stays. This is where we get into those global warming debates, and why you can dump certain things in your sink and other things you can't, and you got to bring somewhere to get them processed. Industrial, this is the business side. These are the money makers, right? And kind of anything can fall under that, but chemistry is definitely a big business, especially right now with Corona. Polymer, so we're getting into rubbers, plastics, things of that sort. Theoretical, these are the guys that are like on the breaking edge. Think of Einstein with his ideas of relativity, right? They're trying to come up with new reasons why things can happen. And then thermochemistry is all about the energy change, the heat, and things like that, because in every scenario we need to account for that. All right. So we got our big topic is really this idea of the scientific method, things that you've heard about before. So the idea is, do experiments fail? Right? Do experiments fail? The answer is yes and no. Right? Experiments obviously fail, but the thing about science and chemistry is we're always trying to learn from those and to create something else besides, right? Besides that failure, so we get to see some of those experiments turn into something that we can use, something that we can produce. So yeah, I guess they fail, but as long as you use that information, it's never failing. All right. So again, you've heard these terms before. So steps to solve. I don't know why my computer's being so slow. Oh man. All right. They popped up because I let my computer catch up. All right. So some of the things, and you've heard of all this before. We're gonna take a big look at number 4. But all of these this year will come up. So making observations, coming up with a question, coming up with an answer, what we suspect is an answer to that question is a hypothesis, testing that experiment, and then analyzing the data. All of that stuff are things that we want to be able to take a look at. But what we're going to focus on is the testing and the experimentation, right? We'll come up with some questions this year, but really it's kind of the fun part is the testing and experiment. But sometimes it takes a lot of work to get there. All right, and then eventually you got to tell us, right? So we'll do that a few times this year, right? That's that lab report, telling me what you found out. Good, bad, or ugly, you're just telling me, right? The better job you do that, the more credit you get from that. All right, here's another look at it. You can see, go backwards. All right, you can see that we have this linear list, right? Ask a question, do background research, construct a hypothesis test. But really, this is just a circular method, right? If it doesn't work, you can always try it again. And that's the point. You come up with a different experiment. Think about Corona right now. There's no way they get the answer right away. And so they're testing, they're trying, they're coming back, all right, how can this work, right? And that's what I want you guys to be able to do. Lots of the labs that we do, we don't have a good enough base in our scientific knowledge to test and retest. But you know what? This year, if something goes wrong and you're like, man, I don't think that should be my data, it's not going to hurt you to retest it, to try again. Just like baking cookies. Man, if your cookies, you make them well one time and not well the other time, you probably just forgot something, right? Baking is just as much an experiment as anything else. So that it doesn't hurt to go back and retry again. All right, so it's the cyclical process. So kind of some of this vocab that we want to know, so you know. Hypothesis, possible explanation, right? It's your answer. I'll ask you that at various points this year. The experiment, I'm going to ask you, sometimes I'll give you the plan. Sometimes I'll ask you to come up with a plan, right? That's hard. Coming up with a plan for an experiment is hard. Independent variables. So these next 3 are the big ones. These next 3 are going to be like what I'm going to be asking you in your little homework. On your Chem quest that we're going to be doing. So independent variable, that is what you change as the scientist, right? The independent variable is how you're going to change what it is you're going to see. So if we're in lab and we want to test how different metals react with different acids, right? We're going to have different metals. Like we're going to change the metal that we put into a certain acid. Excuse me. Where the dependent is more like the data, the observations we take from that test, right? So we change the independent, right? Maybe the metal that goes into it and the acids that go into it. And the dependent is like the what happens. So those can be, visual. Those can be things that we hear. Those could be numbers, right? That we see. The big one is the control, right? The control is all those variables or things that could be variables that we need to make sure are not variables. So the control are the ones that I really want you to start thinking of as we go into it. Anything can be a variable. Anything we can change, right? But in reality, we only want to change one thing to see how that one thing changes what we're looking at. And if multiple things change, we can't say, yes, that is the right answer. This is how we should do it, because the more variables you have that aren't controlled, the harder it is to say, I know I'm right. Right? And that's what scientists are going to do, because saying, I know I'm right is usually worth a lot of money. All right, last topic. We're going to just talk about models, right? The thing about chemistry is we need models, whether they're mathematical, whether they're pictures, whether they're physical, right? We need models to help us see chemistry, because chemistry happens right under our nose, right in our belly, right in our ears, right? Chemistry is going on all around us, and it's hard because we can't see it, right? Physics, we can see what happens when you roll something down a ramp, right? Biology, we can put it under a microscope and get to the basics of what's happening. But the hard part about chemistry and why people struggle with chemistry is everything needs a model, and it's us building those models that people believe that are going to help us out the most. So models can be anything from a mathematical formula to a picture to a just a description of what's going on, right? And so what we're going to use is we're going to use this idea of ozone. You know, how is it formed? Well, here's a model, right? We can put it in words, but we can put it in a picture also. So why is the majority of ozone formed over the equator, right? If you take a look at this model, right, that somebody came up with, we should be able to answer that question, because we have this oxygen, right, that's in our air all the time, and we have these sun's rays, this UV, this energy, right, is hitting them, and as we can see, as it hits them, it splits them, it combines with another O2 in the air, and all of a sudden we get this ozone, right? And we can make that all the time because the sun's always beating down on us, right? That's going to help us answer some of our questions, all right? So ozone, right, is formed from oxygen, O2, the stuff that we breathe. And ozone is so named because it's the Greek word for smell. And if you think about it, anytime you've been out after a lightning storm, right, we get a thunderstorm, you get that fresh scent. Well, lightning, just like the sun, but it does it in a much quicker way because there's so much energy there, that lightning, when it strikes and it's hitting that O2 all around us in the air, it's creating ozone instantly. That fresh scent, that's ozone, right? So why is it important to block UV rays, right? Why is it important for us to block UV rays? We can see down here we have this hole in the ozone that you've probably heard about before. You know, if we were standing in that hole, would that be good for us? You know, the quick answer is no. And why is that? What are the UVB rays doing for us? So we know ozone's a good thing. Obviously, we need it. And the problem with that hole in the ozone comes mainly from things we do as humans. Now, not everything, but lots of it. And if you've ever heard of chlorofluorocarbons or CFCs, right, they're in lots of the products we use, from refrigerators, right? That's why you can't just go dump a refrigerator. To your AC units in your car and things like that. Lots of those are produced with CFCs. And we can see a little picture of what a CFC looks like. Literally, it's a carbon, a fluorine, and 3 chlorines. And what we know is, or what we'll learn, is chlorines and fluorines are very reactive. And we can see through this model, right, taking a look at models of how that disrupts the ozone that we have in the atmosphere, right? So we have these oxygens that are together because we gave them energy, but anytime a chlorine can come in here, right, so that UV, not only does it break apart oxygens and attach a third oxygen to them, but it also is able to take those chlorofluorocarbons that are in the atmosphere and detach one of the chlorines. Well, those chlorines are super reactive, and what they do is they go in, and we can see the model of them breaking it down, which we end up with oxygen, and we end up with chlorine in the atmosphere, which isn't great, right? We can get acid rain and stuff from that. But the bigger problem is the breakdown of the ozone. Okay? So here's just another look of, you know, a factory spilling out CFCs. They go up in the atmosphere. All right? They combine with these ozones, right? And they destroy them, and they turn them into oxygens, right? The bad part about it is just that, right? Whatever we're destroying that we need is going to turn into a problem later on. All right, so I want you to take a second, a couple minutes at the end of this, and just write these down and bring them back to class the next time. just to see what some of our answers are, right? These will I'll ask us, and if you have good answers, that'll amount to some points for you. But how did ozone layer form, and why is it important? Right? Kind of a two-part question. Where on Earth is sunscreen needed the most, right? The more we know about looking at those models that we just took a look at is going to help you out with that. So make sure to go back and take a look at those sections again. You won't need to like have those drawn out or memorized, but being able to answer a question like that through those models would be good. Why is it the closer you get to the equator, darker natural skin is going to be found, right? And then why do Inuit people, so Eskimos, have darker skin? If option number 3 is a reality, why then do Eskimos who live way up north also have the same thing? All right, so take a look at these. Use your notes to try to answer these questions, and we'll take a look at these live.